It's recorded in case I don't feel well on Monday, because I don't feel well now. So I might not feel well on Monday and wouldn't want you to miss out. It's also a bit of a nod to Christmas in May. It's a prelude to Christmas in July. It's really a thing. It's not a thing, but it's a good beanie. Okay, carbohydrates. So we've talked so far about alkenes, alcohols, aldehydes, and ketones. Carbohydrates are like the big grown-up aldehyde and ketone. They just are polyhydroxyaldehyde or polyhydroxy ketone, which basically means that they are either an aldehyde or a ketone with lots and lots of hydroxyl groups. That's all it is, all right? It's simply the same thing. Now, if we are given any structural formula, we should be able to work out whether a molecule is a carbohydrate, and we do that very simply because carbohydrates will always have this general formula, CxH2yOy. Now, that simply means that they might have whatever number of carbons, we don't really care, but the only other atoms they'll have are hydrogens and oxygens, and they'll always have double the amount of hydrogens than they do to oxygens. So all you have to do, count up all the carbons, count up all the hydrogens, count up all the oxygens, and to be a carbohydrate, they will have double the amount of hydrogens than they do of oxygens. Simples? Good. Now, I'm sorry, but you're going to have to fill in your booklet as we go. I tried typing it up to make it nicer for you, as if I was there, but my computer didn't like it, so you're going to have to go with red version. All right. If we've got a sugar, it always contains a simple sugar unit, not a more polymeric version or bigger version. A simple sugar unit will always contain a ketone or an aldehyde functional group, as well as multiple hydroxyl groups. So if we look down here, this is a simple sugar unit. This is also one. Carbon chain, aldehyde group, lots of hydroxyls. Carbon chain, ketone group, because we've got carbons coming off both sides of this group, lots of hydroxyls. So this is glucose, known to its closer friends as a polyhydroxyaldehyde. You can put a space in between. Might make my thing go funny. And this is fructose, known to its friend as a polyhydroxyketone. Let me just check that it's recording. It is. Ooh. All right. So if we have an aqueous solution with glucose, there's always an equilibrium between its ring form and its chain form. Its chain form is down here. Okay, so if we look down here, if you go on to your next page, here's the chain form, here's the ring form. There's an equilibrium that exists between it. So there's a bit of both in there in an aqueous solution. There are three main types of carbohydrates. They are monosaccharides, disaccharides, and polysaccharides. Monosaccharides being one sugar, and so glucose and fructose are examples of those. A disaccharide being two sugars, sucrose is an example of that, and a polysaccharide being something like starch, which is in something like potatoes, for example. Monosaccharides, mono, one saccharide sugar, one sugar. So it's simply a simple carbohydrate with a single sugar unit, one sugar. Now it can exist as a ring or cyclic form, so meaning the same thing, ring and cyclic, or as a chain linear form. We just have to remember, and you should be able to explain this, that a ring form does not have the aldehyde and ketone group. So if you got asked this up here to explain the ability of glucose to react as an aldehyde when in chain form but not when in ring form, all you need to say is that in ring form it does not have the aldehyde or ketone group, and therefore it cannot react as an aldehyde. So therefore in with the Tollens reagent test, where you'd normally form silver, it won't do it. With acidified potassium dichromate, where you'd normally see that colour change from orange to green because the aldehyde formed from a primary alcohol, it was forming a carboxylic acid, and you get a colour change, you won't see that. So you're not going to see, if it's a ring form, you're not going to see those things react. It's a way of determining whether you've got glucose in chain form or in ring form. If we look here, in the ring form, you can see there is no aldehyde group. There's no C double bond O group. There is a CO, but not a C double bond O. You don't need to know the name of that functional group. Now, glucose is a relatively small molecule and it has lots of hydroxyls. It has great ability to hydrogen bond, so it's often a solid at room temperature because it's got great bonding in between the different molecules. Examples are glucose. Please know that. You will if you're doing biology, but you do need to know that. Galactose, fructose, but just know that one. Fructose, you also know the molecular formula for because you know that's a structural isomer of glucose. Then we move on to disaccharides. Di meaning two, saccharide sugar. So it's a carbohydrate unit consisting of two sugar units. Now, this is actually formed by a condensation reaction. Now, a condensation reaction is where you lose water between two monosaccharides. So if you look at this molecule and this molecule, and then you compare it to what's formed over here, we've produced water. Why? Well, if you look here, we've got OH and an OH, right? Over here, we've just got an O. If you're thinking, where does that H come from? That H is actually here. It's just not written. So that H has nothing to do with it. So we've got this OH and this OH, which has formed this O. So therefore, we've really now, over here, got a bond going straight from there to that oxygen. And so therefore, we've lost this OH and that H. And we've lost water. Okay? That's a condensation reaction. When you break down, when you get two monosaccharides, you form them together, you lose water. Right? Condensation reaction, losing water. It doesn't only just happen with carbohydrates, it happens with lots of different reactions. It's a special form of reaction called a condensation reaction. But you can also go back the other way. You can also break down sucrose by hydrolysis into glucose and fructose. And in that case, you're going to actually consume H2O. You're going to add back in H2O into this in order to break up the substance and form glucose and fructose. So it can be broken down into the monosaccharides by hydrolysis with water. So lactose, which you would know as a common thing, for example, you know some people are lactose intolerant. That is actually a disaccharide. Then finally, we've got polysaccharides. Poly meaning many, saccharide meaning sugar. So it's a carbohydrate consisting of many sugar units. And that's formed by a condensation reactions of many monosaccharides, but it's catalyzed by an enzyme. So just remember that extra thing, that when you're forming a polysaccharide, you're doing lots and lots of reactions and you actually catalyze it with an enzyme. Again, they're formed by condensation reactions though. So again, you're losing water all the time here. They can similarly be broken down into mono, di, or trisaccharides, tri meaning three, when you hydrolyze them with water and an enzyme. So with polysaccharides, both forming them with condensation and breaking them up with hydrolysis, you need an enzyme. So if we think of then about the solubility, monosaccharides are small. We now thinking, remember I talked up here, they're a solid, right, because of the extensive hydrogen bonding. But on the other hand, if we're talking about solubility, not talking about solid's a different thing. We're talking about solubility, which is their reactions with or relationship with water. They can undergo extensive hydrogen bonding with the polar water molecules because they've got so many OHs. They are a small molecule, so even though those hydrogen bonds might be relatively strong, they're small. So your water molecules can easily come in and separate them and surround those molecules. So one, you get hydrogen bonding. Two, you do get a smaller molecule and allowing the surrounding of those small molecules with water. Disaccharides, similar things. Many polar hydroxyl groups. It's a small molecule. So you're thinking of the two things. One, it's being it's hydrogen bonding with water. Two, it's small, so water can easily surround and separate. Because those interactions, those strong are not significant. They're not heaps of them. So that enables them to be overcome. With disaccharides, same thing. With polysaccharides, however, you still can do all that hydrogen bonding, but they're large. They're massive, long, big molecules. They've got those secondary forces all adding up are going to be stronger, and it's going to be really hard for a water molecule to surround and separate a big polysaccharide molecule from another one. So they're actually going to not be as soluble in water. All right. So then we have to be able to make sure that we can identify repeating units and draw structural formulas of monomers. So if we think about the repeating unit, you'd have to be able to like draw in these brackets to show the repeating unit. So we have to think, well, how do we know where it repeats? So you basically got to find the pattern, right? Find where it's repeating. And you can see that, say we start at this oxygen repeats itself right there, right? And there, and there. So it'd be important you put the bracket in there, so on the left side of this oxygen, making sure that you put it in here on the right-hand side of that oxygen though. As you can see here, they put it in on the right-hand side of the oxygen, and then the both on the right-hand side there, which is fine. So right-hand side, they're not including either way, the way I said it initially or the way that we've got it here. That oxygen is not included twice, okay? Then you just put a little N down the bottom to show that it's repeating. Now, you can therefore work out what is the actual structural formula of the monomer. If you work out what bonds you have to break, the two bonds that you have to break, so for example that bond and that bond, you'd have to break them in order to form the next substance, then you can work out what the structural formula of the monomer is. Thinking that in order to form the structural formula of the monomer, you'd have to draw this out and you'd have to add in water somewhere. So that would be easy enough to add in water. You'd redraw that and you'd chuck an H there and you'd chuck an OH on that end. If you're going to write an equation of a polysaccharide, you just put the repeating unit in brackets and you put a little N afterwards to show that it repeats itself. And if you're showing it's breaking down, you'd have to add N lots of H2O because you're adding H2O back into it to form that. Vice versa if you were doing the condensation. Okay, there we go. There is the section on carbohydrates.